Welcome to a special 15-year anniversary episode of Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today it's my pleasure to welcome Chuck Black, Senior Scientist and Director of the Center for Functional Nanomaterials, or CFN. CFN is a user facility at Brookhaven National Lab. Before starting at CFN, Chuck was a research staff member at the IBM Thomas J. Watson Research Center, where he pioneered the use of polymer self-assembly as a high-resolution patterning material for the fabrication of semiconductor electronics. Chuck, thank you so much for joining us. Can you tell us a little bit about yourself and how you first got involved in nanotechnology?
Sure, absolutely. And thank you very much for the opportunity to come here and talk about nanoscience, one of my favorite topics. Like you said, I'm the director of Brookhaven's Nanoscience Department, which is a Center for Functional Nanomaterials. And I've been working here at Brookhaven for the last 13 years, I guess getting close to about the halfway mark in my professional career so far. Before I was at Brookhaven, I spent 10 years in the research division of IBM. And before that, I was a graduate student at Harvard, which is really where I got introduced to nanoscience, although we weren't calling it nanoscience at the time. This was the mid-90s, and that phrase wasn't really something that people tended to talk about. So when I was in graduate school, I was working on a PhD in physics, working with Professor Michael Tinkham, who was one of the real pioneers in the field of superconductivity. And as I learned about superconductivity from him, and I learned about how fascinating the phenomenon is, I got interested in the question of, how small could a piece of material be and still be a superconductor? Like, how many atoms does a material have to have before it's a superconductor? And because if you think about it, I guess big pieces of metal, we make wires that are superconductors, but we tend not to talk about single atoms of that same material as being a superconductor. So somewhere in between big and small, there's this change that happens. And that's what I spent my PhD thinking about and trying to answer and making some progress. But that's kind of, in some ways, the essence of nanoscience, right? Is the idea that at this size scale in the range of nanometers, the properties of materials change. And I guess you would say that's where I got my start, and I've been thinking about those kinds of questions ever since.
Drilling down a little bit into the center itself, can you talk about some of the unique tools that are available at the Center for Functional Nanomaterials and some of the projects that maybe take advantage of these tools?
Yes, absolutely. So when I came to Brookhaven 13 years ago, I came to be a part of this center. The center was still in the planning stages at that point, but the vision that the Department of Energy had was that there were going to be facilities dedicated to nanoscience and offering capabilities to help people as they pursued their interest in this field that was just kind of starting out, or at least the phrase had just been coined around that time. And the center was meant to be a place where we collected together unique capabilities and unique scientists with very specialized sets of skills, and tasked them to do two things. And it's this dual mission that I think really makes the CFN a unique place. Because honestly, the real answer to your question is that the truly unique things that we have here are the people, the staff that we have working here. And I say that they're unique because we ask them to do two things, which typically is hard to find in a single person. On the one hand, we want scientists who believe they're the best at what they do. Whatever their particular area is in nanoscience, we want them to believe they're the best. But we also ask them to be willing to put all of that aside when it's time to help a user. And when a user comes here, we are to treat them as if their science is the most important thing, and to use all of those same talents to help them achieve their goals. It's this double mission that's helped us collect together a staff of really talented people who at the same time are nice. And they enjoy working with other people. They enjoy helping other people. They enjoy lending their talents to helping other people solve their problems. It's a fantastic place to work, and it's the people. It's the people. So that's a cop-out answer, I know. Like, the real thing you want to know is, what machines do you have? And I'll keep telling you, yes, we have machines. Yes, of course we have machines, but we also have people. But let me tell you about some of the machines. We have spent time and effort thinking about the types of capabilities that can really, truly enable nanoscience in new directions and that aren't just available everywhere. That's kind of what we're supposed to do. And the set of instruments that we maintain and support often have this similar characteristic, the idea that to truly understand materials, you would like to be able to measure them at high resolution, whatever that means, measuring where the atoms are or measuring fine structure in their spectroscopy, whatever that means, at high resolution. But you want to be able to measure that while the material is doing whatever it's supposed to be doing. There's no better way to tell if a catalyst is working well and understanding why it's working, to be able to watch it while it's catalyzing something. So we have designed a set of instruments here we call operando characterization. So it's meant to imply that you're watching the material do its job. And the reason that is so challenging and so unique, usually to be able to watch something at high resolution, you really need to leave it alone. You need to put it in some kind of isolated environment where it doesn't shake and it doesn't interact with anything, because if it moves, you can't watch it as closely. And so it's this combination of high precision characterization coupled together with the ability to measure it precisely that really is a unique aspect of many of the facilities that we support.
Can you give us an example of a project that you find particularly interesting?
Yeah, I would love to. I have my list. I made my list. But I'm going to go with the one that I was just talking with a scientist this morning about, because it's something that I'm still blown away by it. I was down this morning speaking with the researcher who supports this instrument that we have, and it's a type of atomic force microscope. This particular type of microscope has been modified by the researcher because he spent his career doing this kind of microscopy. It has the ability to image organic molecules kind of with atomic resolution and even subatomic resolution. Like, I'm seeing pictures come out of this microscope, the likes I've never seen. So he's studying small hydrocarbons, but if you've taken any chemistry, you know what a hydrocarbon looks like. It's got the benzene ring with the little H's hanging off the ring, and we've all seen pictures of them, and I've always just imagined that they're pictures. And lo and behold, this microscope is taking pictures of these molecules, and they look just like the book. Like, I've never seen a microscope able to do that. I mean, it's I could go look at it every day because it's so amazing. Now, the project I'd like to tell you about, the scientist was so happy this morning. He's working with a user, and it's a user from ExxonMobil. And believe it or not, what this user helped us learn was that there are still things in crude oil that people don't know what exactly is in crude oil, because there are all these small hydrocarbons, variations of 3 benzene rings, in some are slightly bent, some are not, but it's impossible to tell them apart by any other spectroscopic means. And lo and behold, this microscope can tell them apart. So you can put little tiny amounts of crude oil on a surface, spread out the molecules, and you can see them, and you can see these very subtle differences that are impossible to see by any other means. And the idea that we've created an instrument that can help make progress on a pretty practical problem that is being addressed by a pretty large company, it's a nice feeling of satisfaction.
One of the things that we hear very often about the NNI is that in the early days, and you've been there as they were beginning to put together this center, working across discipline boundaries was really novel. And the interdisciplinarity and the approach of bringing different people together to solve problems is really the way we tackle a lot of problems now. and that's the way science is often done. What are your observations from your perspective there at the CFN and more broadly in your experience in research?
Yeah, I'm glad you asked that question because it touches on one of my favorite things to do when I'm trying to give an overview of what our center is about and why it's so exciting to work here. And I guess I would also say why it's so fulfilling for me and for our staff to work here. And I think it stems from exactly your point, that it's the fact that nanoscience has a promise to impact so many different areas of science. And in working in a center like that, you as a working scientist have a chance in your career to touch many different places. One of the slides that I show and one of the stories that I tell is I put up a set of titles of papers that our users have published from the prior year. And I say, just look at this. And, the first few titles in the list are things you might expect. Maybe a user was working on solar cells, or maybe they were working on batteries or microelectronic, kind of the things that traditionally we associate with nanoscience. And so I show people those, and usually people are kind of nodding along and saying, yeah, makes sense. And then I say, but look at this. This user published a paper. They were working on a material that you could make cement from that just when it's sitting out in the air, it would soak up pollution. And this user was working on trying to make alloys that would be more radiation hard, that you could be used to line a nuclear reactor with. And then I say, and these users were working on medical devices. This person had an idea for early detection of ovarian cancer or sickle cell. And these were all titles of papers that people came here and we applied our skills to help them solve those problems. As a scientist, I don't know the first thing about detecting sickle cells or making pollution-eating cement. I don't know anything about the science of those. But the techniques that were used to help those people achieve their mission, I do know about those, and I can apply my talents to those. So for me, the reason it's so fulfilling here is because I'm working on my science. I'm going to do my narrow thing. But when I look back on the totality of my career, I can say I touched so many other things.
Well, that's great. And I want to just carry that forward a little bit, looking at not only the interdisciplinarity and the ability to work across boundaries, but technically speaking, what are some of the advances that you have observed over the past 15 years? And where do you see the accomplishments that have been enabled by this field of science?
Yeah, I know. I think in terms of technology, if you kind of think about all of human beings like successes, like it's really hard to top semiconductor microelectronics. Like the pace of progress and the level of technical complexity that goes into these things that are so essential to everything in our world, it's really hard to imagine anything more impactful. With all due respect to all of the medical advances, semiconductor technology is just outrageously hard and outrageously successful. And that's kind of fundamentally nanoscience there. They've been doing nanoscience longer than anyone.
So I want to thank you again for taking the time to chat with us. And I want to ask, do you have any closing thoughts that you'd like to share with our listeners?
The DOE user facilities are fantastic. They're staffed with super talented people whose job it is to help. In my opinion, the DOE does a great job of building facilities, staffing facilities, but we don't do a good enough job at advertising our facilities. And so these are resources meant for everyone, and it's something that as a society we should be proud of. We should be proud that we think that this is so important that we're willing to pay for it. And so now that we've done that, we want to take full advantage of it.
Thank you for joining us today for this special 15-year anniversary edition of Stories from the NNI. If you would like to learn more about nanotechnology, please visit nano.gov or email us at info@nnco.nano.gov. And check back here for more stories.